Hello everyone, my name is Ahmed and Saad. I'm a PhD student at Paris-Saclay, and today I'll be presenting the work done with Gabriele, Facciolo and Axel Davy called On the Importance of Large Objects in CNN-based Object Detection Algorithms. So it all started with a very simple yet not very explored question in computer vision, which is what is the influence of object sizes on the performances of object detectors? The idea of different object sizes having different influences in terms of learned representations or in terms of impacts on the later performances across all sizes. It is not very explored, and we wanted to explore this idea, and we wanted to see whether the network focuses on large objects and small objects in a different way, and whether there is something to benefit from it. So we started with when we try to answer the first question, the simple experiment to do is to take any object detection dataset, such as COCO in our case, and we divide it into small, medium, and large objects categories. And the idea here is to pre-train and fine-tune YOLO v5 on different object sizes and compare the results. So we want to see the differences between the features learned from small, medium, and large objects. So what we want to do is we want to pre-train YOLO on different object sizes, and then freeze the encoder, so to freeze the representations, and then fine-tune on the whole dataset, on the whole COCO dataset, to see whether the learned features from object sizes contribute differently to the overall score. So, and these are the results that we obtained. So the idea here is that the reference scores, so when we train on the whole dataset, is always the best score in our case. It's better than pre-training on any object sizes, and this means that discarding objects of any size degrade the performances. So that means that the model needs all object sizes in the training to be performant on all the object sizes during validation and testing. The second thing that we have that we can observe in these results is that also the fine-tuning step is very important, because in the fine-tuning step we introduce all the data set with all object sizes, and this confirms the fact that all object sizes are needed in order to get the best performances we can. So we see it here when we pre-train on small and medium and then fine-tune on all data set, we obtain better results across all sizes. And then we see it also on large objects. Now, the most intriguing result, or the most curious thing that we can observe here, is that the fine-tuning, when we fine-tune across all the data, we see that the models pre-trained on large objects perform better, not only on large objects, but also across all sizes. And this is a very curious result. This means that the feature learned from large objects in the pre-training led to better performances when we fine-tuned on the whole dataset, and this across all sizes. So this means that the representation learned from large objects maybe are more generic, with respect to the object sizes, but only as a helper for fine-tuning. We also need the small objects in our training dataset in order to get the best results. Now, one possible explanation is that the large objects contain more pixels and so more informations, and also they are less dependent on the context in order to be identified. We can do a quick visual experiment on this. For example, if we take those three small objects, we see that in the first row we take them without any context. In the second row, we take them with small context, and then we can see them in the whole image, or in the entire context. And we see, for example, in the second image, which is an image of a clock hanging on the wall, even a human eye cannot discern that it is a clock without the presence of its entire context, which means that there is a room or a kitchen maybe, and then something is hanging on the wall, and it is a clock. The same thing applies for the book here in the last row. You see that taken apart, we cannot identify the object. In the second object, we can see, yeah, maybe they are books, maybe they are CD shelves, etc. But when we take the whole image and the object is here, we can clearly see that it can only be a book. So this means that small objects depend a lot on their context in order to be correctly identified, and this does not apply for a large object. For example, if you take a TV here, the TV here, and you take it apart, it will be a large object, and you can discern that it is a TV without the need of any context. So these are curious results, these are interesting results, but how can we benefit from them? So the first idea, or the most straightforward idea that came along, is that we want to force the model to focus more on large object during training without removing the small object from the training. So one possible solution is to introduce the weighting function for the loss, and this weighting function is calculated with respect to the object size, for example, its area, and we want to weight each object in the loss with its weight. So in our case, what we used is we used a weighting function of log of the area of the object. As you can see here, we normalized the weight across the batch, so we get weights between 0 and 1, and then we applied this function on each loss term on each object that is whose loss is being calculated during the training. So this has many effects. The first effect is that if you see, for example, the ratio of small and medium and large objects without the weights, so it's the simple ratio and the weighted ratio, we can see that this table shows that the balance on COCO and UScenes, which are the two data sets used in our entire experiments, the balance is heavily shifted towards large objects. So the weighted ratio of large objects, even though they are a minority here in both data sets, the weighted loss gives them more weight, and so they are more impactful on the training. We can see also see this, for example, too, when we measure, the ratio of the sum of gradient amplitudes over the first 100 epochs for large and small objects. So we take this quantity, which is the sum of the ratio of the gradients of large objects with respect to the model parameter, over the same quantity calculated on the small object. This is a good approximation, a good yet a little bit vague approximation of the impact of the updates of the weights updates, and we can see that the introduction of our weighting function gives a larger impact for the large objects on the weight change. And the third thing, is a result of all of this. So basically, when we use our weighting function, the scores in mean average precision and recall are improved for many models across all object sizes. You can see here the example for COCO, and on the article you can see the result tables for new scenes. So one thing that we wanted also to see is whether we chose the best weighting function for this task. So the idea here is that we tried 3 different weighting functions, as you can see here. So we got the best results with log of the area of the object, but this doesn't mean that log of the area of the object is the best function. Maybe there are some better functions to consider, but in our small pool of tested functions, we saw that log of W times H is relatively good compared to the others. Also, we wanted to do a little ablation study on the effect of putting the weighting term in each loss term. So as you may know, so the loss function in every object detector generally is composed of classification loss, which is used to classify each object, and then the detection loss, which is basically the loss for correctly localizing and detecting whether there is an object or not at first, and then localizing the object with a good bounding box. So we wanted to play with the weighting function. So each time we put it, whether on the classification part of the loss or on the detection part of the loss. And as you can see here, the best results are given when we have when we have the weighting function applied on both classification and detection losses. So as a conclusion, the presence of large objects in the training dataset helps to learn features that yield better performances also on small and medium objects. And we can benefit from this by introducing a weighting term that forces the network to focus more on the large objects. Also, future research in this area maybe can investigate novel strategies that may be better in considering the impact of large objects on detection accuracy across different object sizes. So thank you all for your attention. I'd be happy to take your questions.